So one thing mathematicians like to do is they like to ask themselves some weird problems and some interesting problems and see what they can find out about the things they have discovered using these problems. So one problem that mathematicians have is they have two vectors. They have this vector here that is 3, 1, and they have this vector of 1, 2 here. And they say, I am going to call the bottom vector, this one over here, this is going to be the ground. And this is going to be a person. Kind of funny looking person, I know, but it'll do. It's a very it's an arrow person. So the arrow person is standing in the sun, and because the person is standing in the sun, they're casting a shadow on the ground, and it's exactly at a 90-degree angle to the ground. That is not 90 degrees, I apologize. And they want to know what is the length of this shadow. So the shadow is right here. What is that length? Well, where we left off yesterday, we just found out how to find the cosine of this angle over here. And as a review, to find the cosine of the angle between two vectors, I am going to call these, what should I call these now? Okay, so to find the cosine of this angle, it is going to be the dot product of the peace sign and the flower over the length of the peace sign times the length of the flower. Okay, so we know how to find that angle, the cosine. So maybe we can use this. Well, let's see, we know the cosine is going to be the shadow. So the cosine theta is going to be the shadow over the hypotenuse. And the hypotenuse here is the length of the peace sign. So shadow over the length of the peace sign. So if we want to find the shadow, all we need to do is multiply by the length of the peace sign. And that gives us shadow equals the length of the peace sign times cosine theta, which we can also just write as peace sign, the dot product of peace sign and flower over the length of flower. So this weird shadow thing, that's an interesting thing. And what mathematicians call it is the component of peace sign in the direction of flower, or the component of peace sign along flower. But that's a really long and complicated name. I think shadow function works great. So the shadow of peace sign on the flower. Because then you know exactly what it is, right? But there's another function, and that is very similar to the shadow, except this time you're not just trying to find length of the shadow, you're trying to find exactly the whole vector. So that's the length and the direction. But you already know the direction. The direction is going to be the same as the flower because the direction it is on the flower. So how do we shrink the flower to make it the length of the shadow? Well, we can look at some examples of shrinking and growing stuff. So if I have a vector over here and I want to stretch it out, so I've just doubled the size, and since you multiply the horizontal component by 2 and you multiply the vertical component by 2, we can see that to stretch something by 2, you just need to multiply the vector by 2. So the same thing works here, where in order to shrink this, you just need to multiply it by the length of the shadow. And we already have the length of the shadow based on our shadow function. So what mathematicians call the projection, because imagine you have a projector and you're trying to project a 3D object onto this line, or onto this vector, the projection of the peace sign along the flower is just going to be the shadow times the flower. And notice that you can multiply here, because even though you cannot multiply vectors by themselves, you can multiply vectors by the numbers, because multiplying 1, 2 by 5 is just going to be 5, 10. You just multiply it by each of the numbers. That's pretty simple. You can multiply it by a number, and in this case, we're multiplying it by the shadow. So if we expand this all out, that's going to be the sorry, this should be flour. Okay, so we multiply, so we make the flour the length of the shadow, which is the same thing as multiplying flour by shadow. So if we expand this out, that's going to be the length of the peace sign times the cosine of the angle times the flour, or that can also be written as the dot product of the peace sign and the flour divided by the length of the flour. And remember, this whole thing is just a number or a length. This is not going to be a vector at all, because once you take the dot product of these two, that becomes a length, and this is the length of the vector, so that's also going to be a length. And then you just multiply that length by the flour. So either way, you have the shadow function that gives you the length of a shadow, and you have a projection that gives you the whole vector of what the shadow is going to look like. So those are pretty interesting things. See what you can do with these. And if you come up with any interesting like drawing or project or mathematical thing that you can do with this, let me know, because I would be pretty interested in seeing. Now, besides projections, what else can we do with vectors? Well, one of the most common applications with vectors are in physics, with forces. Because the thing about forces is that they have a strength instead of a length. Now we are dealing with the strength. They rhyme, but they are not the same thing. So we have a strength, and we have a direction. So it's really useful to use in physics vectors representing things. And now this is going to be a really basic explanation, mainly because I don't have any physics background at all. But here are some ways that you can use vectors in physics. So say you have a force on this point. I'm going to call it a point because it would complicate things if different forces are acting on different things. But you can imagine it's a ball, and all the forces are acting on the same part of the ball, because I don't know how to deal with forces acting on like different parts of the ball, but okay. And you have this force that pulls it up. And we can say it pulls it up at a unit of 50, whatever 50 is, straight up. But then we also have this force. See, two people are playing like tug-of-war with this ball. We have this force that is pulling it down, also by 50. So in vector form, so the length of this is 50 and the length of that is 50. So in vector form, this vector would just be, it's going across 0 and up 50. And this would be going across 0 and down 50, or up negative 50. So to find the total force acting upon the ball, you just add the two together. And that gives us a total force of 0, 0. And that kind of makes sense, right? It may not seem like, oh wow, if you have two strong forces pulling on something, it's going to be like no force. But if you think about it, if you have a ball and two people are pulling at it at exactly the same strength, it's not going to go anywhere. It's just going to stay exactly where it is. But what if you have this side being slightly stronger? Let's say it has a strength of 60. Now, the overall force of the ball is going to be 0, 10. So it's going to move 10 up. And that kind of makes sense too. Because if you have two people and they're pulling at one object, but one person is stronger than the other, then the stronger person is eventually going to get the object, just because they can pull harder. But what if you have things that are moving in different directions than just opposite each other? So what if you have someone pulling it in this direction and someone else pulling it down? Now we're dealing with vectors, so if we have this moving down at 50 units and that moving in this direction at 50 units, say this direction, now because we are dealing with vectors, we need to know exactly what the direction is. So numerically, I'm going to say that is about 45 degrees from whatever the horizontal is, right? So in order to write these vectors in component form, it's really easy to write this one, because this one just becomes 0, negative 50, because it is going across 0 and down 50. But what about this? Just because we know its length doesn't mean we know its component form. But the thing about 45 degree triangles is you know that these two sides are the same. And you can either use the Pythagorean theorem here with x squared plus x squared equals 50 squared, or if you just know the identity that this should be a 1, 1, root 2 right triangle, then you would be able to find out that this is 50 over the square root of 2, which is equal to 25 times the square root of 2. So it is going across 25 times the square root of 2 units. It's also going up 25 times the square root of 2 units. So that's 25 root 2, comma 25 root 2. Now you notice in total, this one's pulling it across not at all, and that one's pulling it across 25 root 2 units. So overall, it's going to go across 25 root 2 units, and this one is pulling it down 50, and this one's pulling it up 25 root 2, which well, I'm not gonna round that because rounding is gross. Okay, I am a theoretical mathematician. I do not like to round. And this is 25 root 2 minus 50, which is going to be slightly negative. So then we can see that since this one's not pulling it across at all, but this one is, it's going to move slightly. It's going to move across, however much this one is pulling it across. Or this one's pulling it straight down, and that one's pulling it up at an angle. So then because of this one is pulling it overall, it's pulling it up less, and this one's pulling it down more, it's going to move slightly down. So that's going to give us something like this. So overall, the force on the point is going to look like this blue arrow. So it kind of, the combination of two forces is the addition of two forces. And that's gonna look like they both combine together and they both pull it, but sometimes they counteract each other, which means sometimes the forces actually get less, as in this case, the upward force is less than this upward force. But overall, it's just the combination or the addition of these forces. So that makes the forces pretty simple to deal with, because all you need to do is add them together. Okay, so I'm going to look at one final problem here involving trig, and this problem I'm going to look at more theoretically just because I don't feel like doing computations right now. So, let's look at this problem. So you have a ramp here. So you have a ramp here. I don't know why you have a ramp. Maybe you're like a skateboarder and you're like skateboarding down stuff. Or maybe you're just like throwing balls down ramps for whatever reason. I don't know. But anyway, you have a ramp and you have this ball. And the ball is going to be rolling down the ramp, right? When you put a ball on an incline, it rolls down. Now, why does the ball roll down the ramp? Well, there's no force pushing the ball diagonally, but there is a force. The only force acting upon it is gravity. Gravity is what pushes the ball down the ramp. So, but gravity just pushes the ball straight down. So we can write that as a vector that goes straight down here. And now what is the magnitude of this vector? Well, gravity is dependent on, well, the way we are going to use it, the magnitude of this vector is just going to be whatever weight the ball is. So I'm going to say weight. And this one is weight and not mass because we are dealing with gravity here. But yeah, so we just have this one force of weight that is pulling it down. If we say this is a 5-pound ball, maybe it's a really heavy ball, then it's pulling it down 5 pounds worth. Whatever that means. But how much is it actually getting pulled down this way? Well, to do that, you know how in the previous problem, we took two vectors and we combined them to make, we took two forces and we combined them to make one total vector force? Well, we can do the opposite here, where we take one force and we split it into two separate vectors. So we have one vector that goes down this way. And this vector is just going to be the projection of this weight force onto this line. So that's how you know how far this is. So again, that would be the shadow times the vector of the incline. And again, for the incline vector, you only need the direction. For the incline vector, you only need the direction, so it doesn't. So you can make up units for. Wait, actually, don't make up units. That's a bad idea. So you can just use the units of, say, a circle. You can just use the units of a vector that has like a magnitude of 1 and multiply it by the length of the shadow to find out like how the vector of this one going down. But when you split it into different vectors, you can't just split it into one vector that's going into a completely different direction. In order to make up this full gravity force, you will also have to have a vector that is perpendicular to the incline. And this one is going this way. Or you can also just say it's going this way. Doesn't really matter, but it is technically coming from the ball. So I guess. But again, the location of a vector does not matter, only the length and the direction. So we can look at this vector here. Well, what direction is the vector? Well, that's simple. It's perpendicular to whatever this is. So you can use the fact that it is perpendicular to either find the angle, or you can use the fact that it is perpendicular and use the fact that vectors that are perpendicular have a dot product of 1 to find the angle in terms of like sine and cosine. Or to find the sine and cosine of the angle, so you already have it in component form. But how long is the vector? Well, if you have any imaginary vector that is perpendicular, then again, you can see that you just take the projection of this vector onto this vector, and you will get a vector of the length that you want. So again, in order to find out how much gravity makes this go down, you just take the projection of the gravity vector onto the slope vector. And then you can make a vector that is perpendicular, and again take the projection of the gravity vector onto the perpendicular vector. And then you have two vectors, and you should be able to, and if you want to double check your work, you should be able to add the two vectors because their combined force should equal the force of gravity. So that's a little bit of theory on how a ball rolls down a hill, and I hope that helps you do the calculations part, because again, calculating is gross, theory is great. But besides that, for now, that's all, and I will see you next time!